All right, howdy y'all. So we got, in this video, we've got a 10 and a 11. And so what we're gonna be covering here is that convolution, sorry, cat is trying to mess with my computer. So convolution preserves smoothness in a sense. So what we mean by that is that if I take the convolution of f and g, the convolution of f and g will be at least as smooth as f and g were. So to formalize what we mean by this, we're going to need a couple definitions. So first off, we need the concept of a multi-index. So a multi-index alpha is going to be an element of nn. So I can write alpha as equal to a vector alpha 1, alpha 2, up to alpha n, where each of the alpha n's are natural numbers, and then I can define the partial derivative with respect to alpha. What this is going to mean is that I have the partial derivative with respect to each of the variables in our space with the alpha ith partial derivative with respect to each xi. 2 alpha 2 partial with respect to xn to the alpha, right? So this is going to be, in a sense, we say that the magnitude of alpha is equal to the sum of alpha i's, right? So in this sense, if alpha is less than k, then then the sum of all these will be less than k, which means that since g is in ck, the partial derivative alpha on g makes sense, that this is in fact differentiable. So what this is saying is that if g is k differentiable, then the convolution will be at least k differentiable also, because I can pass it through, right? So what we're going to do to think about this is that we have the convolution of f and g. Here I did gf, but same thing. So if I'm going to take the partial with respect to alpha, this integrals with respect to y. So the partial derivative is with respect to x's. We can pass that through here. Now I can take the partial derivative here because g is in fact partially derivable, and because g is bounded, the product of these two is bounded. Or sorry, the partial derivative. Sorry, this should be the partial. Alpha is bounded. So because this is bounded, the product of a bounded function with an L1 function is in fact going to be L1. So this thing exists for all y, which means that we can treat this as the first function of the convolution, and we get that it is equal to the convolution of the alpha partial derivative of g convolution f. So this guy obviously being equal to alpha g convolution f, right? So this tells us that the convolution preserves the greater smoothness of whichever two functions, of the two functions being convoluted. So for 811, we're going to consider infinitely differentiable functions. So if I have two f and g that live in S, then the convolution of f and g live in S. And what S is something from the section before, so it's defined to be the set of C infinity functions who have the n alpha norm is finite for all n and for all alpha. Here, this n lives is a natural number, right? So, is that a natural number? I think so. Okay. One second. Yeah, n is a natural number. or 0, actually. The book says it can also be 0. So we have this norm here, and we define this norm by saying that's the supremum across all x's in Rn, with 1 plus the absolute value of x to the n, and then the alpha derivative of fx. So what we get is that S, if this thing is finite for any choice of n and alpha, and then f is obviously infinite differentiable because it doesn't make sense for certain alphas if it's not infinitely differentiable. So if we have two functions that live in this space, then their convolution also lives in this space. So what we're going to get, first off, is that the convolution obviously lives in this, in C infinity. So this part makes sense. The question is just, is this finite everywhere? And the reason that we know that the convolution lives in here is because of part B, or the first one, 8.10. So what we do then is we consider 1 plus x, the absolute value of x to the n, times the alpha derivative of the convolution of f and g with respect to x. And again, we're taking the absolute value of this guy. Then what we notice is, down here, is that 1 plus x, the absolute value of x, is going to be less than or equal to, 1 plus x minus y. So we're just splitting, using the sublinearity of absolute value to split, or sorry, of the norm in Rn, to split it across y. So we take away y, add y, and then split using sublinearity. And then we notice that this thing here is in fact less than this product. And that should be obvious just by foiling this out, that this ends up with 1 extra. So what we get is that I can then write this convolution here out, and at the same time pass in this guy here as a product. So what we're going to get is that if I take the nth power of this guy, then that's just going to be the nth power of these two. And then we can split those across the f and g. So first, we take the convolution, we get fx minus y, g, y, and then again by the first part, I can pass the partial derivative inside. This time I did it with g because g was the ck function, but here both of them are infinitely differentiable. So what we get is that I put it on, apply the alpha partial derivative to fx minus y, and I put its coefficient being this term here, whereas g gets the coefficient of this guy. Now, what I get is that this thing here is less than fn alpha, because it is one of the things taken in the, because it has to be, all of these have to be finite, and it's going to be the supremum across, one second. All right, so we know it's finite, and then we take the supremum across all of the x's. So this guy is always going to be less than that one. Then secondly, g is going, this 1 plus y to the n, absolute value gy, is going to be less than, and then we do this here. So what we're actually going to do is we're going to replace this n. We're going to split this n into two different ones. The first one is going to be n is equal to n plus little n plus 1 minus n minus 1. So when I pull out the big N plus 1 here, and again, we get 1 here because we're not taking the partial derivative of g. The book actually has an alpha here, but that's a typo. So note in the proof, they accidentally put out both alphas here, but there's only one partial derivative because the partial derivative only applies to one of the two functions of the convolution. So when we do this, we can break this guy up into two separate terms, this one and this one, and what we're left with is 1 plus y to the negative n minus 1. Now, we go back to chapter 2, and I believe it is 2.53. It says that if we can bound them in a certain way, we can show that a function is in fact in L1. So we take a unit ball, or not necessarily a unit ball, but a ball around the origin, and then we consider two cases, it inside the ball and it outside the ball. And then we show what the theorem says is that, so I've got 1 plus y, which is the thing that we're working with, and I have n plus 1 is greater than n. And here, we're concerned with the negative of the exponent. So we have negative n minus 1 is going to be less than negative n. So what we show is, since 1 plus y is greater than the absolute value of y, and we're taking that to a larger negative exponent than this one, then this guy is in fact going to be smaller than this is going to, in fact, be smaller than y to the negative n because it's larger and its exponent is larger in magnitude on the complement of the unit ball around 0. And the reason that we have it on the complement of the unit ball around 0 is because what we have to show is that for a larger exponent, a more negative exponent, the function is less than a coefficient times the variable to the dimension of the space. And we're in Rn, so here we have n. So this shows that this function is in fact in L1. L1 of the complement of the unit ball. Then, to show that it's inside that it's also L1 inside the unit ball, what we have to show is that it is greater than, that it is less than, that the function is less than a constant times the variable to a number smaller than the dimension. So here what we do is we say that 1 plus the magnitude of y is greater than 1 for all y. So we get that it raised to a negative integer is going to be less than 1. However, the reciprocal of the magnitude of all of the vectors inside of the unit ball is in fact greater than 1 because their magnitudes are smaller than 1. So this guy is bounded by 1 times the reciprocal of its variables. But 1 is obviously less than the dimension of the space because we're in Rn, which gives us that this guy is also an L1B0, which means, L1 of the unit ball in Rn. So because it's in L1 of the unit ball and it's in L1 of the complement of the unit ball, it's in L1 of Rn in general, which means that this integral here is finite. But since this guy here is finite, and obviously both of these are finite because of our assumption that f and g were in S, and that's in fact the definition of being in S, we get this whole thing is finite, but this right here is exactly what we needed to show was finite for all n in alpha for the convolution to be in S. So this proves that this guy is in S as desired. Okay, so a lot of technical details there. Covers about 3 sections worth of material for little details in the proof, but it's a very rewarding theorem. And if you want to look at a little bit more in detail, if the steps of this were slightly confusing, go back and look at the full statement of the theorem 2.53, where it shows exactly what the requirements are to show that something is in L1 of a ball centered at 0 and the complement centered. Okay, anyway, I will see you guys in the next video with 8.12.